Hello, students. Welcome to this lecture. So, in this lecture, we will start probability theory. So, this is our first class. So, in this class, we will cover inside section 14.1 and 14.1.1 to 14.1.5 and example number 1 to 3. Okay. So, this is disclaimer. So, first, we will cover what does mean event. Okay. And then we will discuss 14.1.1 occurrence of an event. So, how an event occur, uh, that's about we will discuss. And then we will discuss types of events. So, there are some types of events like impossible event, CO event, simple event, compound event. Okay. So, we will discuss about this. And then we will discuss in this lecture algebra of events. In set theory, we already studied about complementary, union, intersection, and difference operation one sets. Okay, and similarly, we will study algebra of events, complementary events, union of two events, intersection of two events, and difference of events. Okay, and then 14.1.4 we will discuss mutually exclusive events. So, what does mean mutually exclusive events? So, we will discuss about this, and then we will discuss exhaustive events. So, there we will discuss definition of exhaustive events and example of exhaustive events. And lastly, we will discuss example 1 to 3. Okay. So, students, make sure you have with your notebooks and pens ready. So, let's start. So, we have studied about random experiment. So, try to recall what does mean random experiment. What is the definition of random experiment? So, definition of random experiment. So, a random experiment is a process where the outcome is not predictable with certainty, but all possible outcomes are known. Okay. So, in random experiment, which outcome will come, we cannot predict in advance, but the possible outcomes we already known. Okay. So, for example, flipping a coin. So, if we flip a coin, then there are two possible outcomes. One is head and another is tail. Okay. So, in advance, we have known the possible outcomes, but after flipping a coin, which outcome will come, we don't know. Okay, we don't know we in advance. Okay, so this experiment is called random experiment. So flipping a coin is a random experiment. And what is the definition of sample space? So we have studied about sample space in our previous in our earlier classes. Okay, so what is the definition of sample space? So the set of all possible outcomes of a random experiment is called sample space. Okay, sample space is nothing but a set of all possible outcomes in a random experiment. Okay, so we have studied about random experiment and sample space associated with an experiment. Okay, so the sample space serve as an universal set for all questions concerned with the experiment. Okay, so now we treat sample space as an universal set. Okay, and students, we you all know about universal set. Okay, so you have studied about universal set one set chapter. Now consider the experiment of tossing a coin two times. So we are considering here that experiment. Okay, that is basically we are tossing a coin two times. Okay. And what is the associated sample space of tossing a coin two times? So an associated sample space is S. Okay, S is basically equal to set H comma HT comma TH comma TT. Okay, so if we toss a coin twice, then we might get double head. Okay, we might get one head and one tail. Okay, so in first toss we can get head, and in second toss we can get tail. Okay, in other word, uh, if first toss, okay, in first toss if we take tail and then we get head, okay, then we write it th. And if we toss a coin two times and then if we get as an outcome tail, okay, so in first toss we get tail and in second toss we get tail, okay, then we write that element as tt. So the sample space S is basically equal to HH comma HT comma TH comma TT. Okay. So this is our sample space of tossing a coin two times. Now suppose that we are interested in those outcomes which correspond to the occurrence of exactly one head. So here we are interested in those outcomes which correspond to the occurrence of exactly one head. So try to observe here in sample space S. So how many such elements you will get in S where exactly one head you will get? So we find that H, T and TH. Okay, H, T and TH are the only elements of S corresponding to the occurrence of exactly one head. Okay, exactly one head in HT and TH. So HT and TH are the only elements of S. Clear? So these two elements form the set. Okay, and that set is we denote here E. So E is nothing but set HT comma TH. So here E is a set. Okay, you can say E is a subset of set S. Okay, sample space S. And we know that the set E is a subset of the sample space S. Okay, so here you can prove E is subset of sample space S. Why? Because every element of the set E belongs in set S. Okay, sample space S. So E is a subset of the sample space S. Similarly, we find the following correspondence between events and subsets of S. So here in this table, see, in left hand side we have given description of events. Okay, and in right hand side we have given corresponding subset of S. Okay, so read this. Number of tails is exactly 2. So look at this sample space S. Okay, and find that elements where number of tails is exactly 2. Okay, so that type of element you will get basically TT. So TT is the only element of S corresponding to the occurrence of number of tails is exactly 2. Okay, so corresponding subset of S is basically A equal to TT. Clear? And then see here a number of tails is at least 1. So at least mean, so there might be one tail. Okay, there might be two tails, but at least one tail should be there. So number of tails is at least 1. So here you will get HT, TH and TT are the only elements of S corresponding to the event number of tails is at least 1. Okay, so the set B subset of is B is basically HT comma TH comma TT. Okay, and then find number of heads is at most 1. So find that element of S which are where number of heads is at most 1. Okay, so we find that HT, TH, and TT are the only elements of S corresponding to the occurrence of number of heads is at most 1. Okay, so subset C of S is equal to HT, comma TH, comma TT. Okay, and then see here, second toss is not head. So second toss cannot be head. So HTTT, okay, are the elements of S corresponding to the occurrence of second toss is not head. Okay, so the D is basically subset of S, and D set can be written as HT, comma TT. Okay, and now you can find number of tails is at most 2. Okay, the set S is basically HH, comma HT, comma TH, comma TT. Okay, number of tails is more than 2. Okay, so there there is not possible to get number of tails is more than 2. Okay, so we can get at most 2 tails. So there is no more than 2 tails. Okay, so number of tails is more than 2 is impossible. So corresponding subset of S is basically phi. Clear? Now this suggests that a subset of sample space is associated with an event. Okay, and an event is associated with a subset of sample space. So we connected we are connected here event with sample space. So an event is associated with a subset of sample space. Okay, and a subset of sample space is associated with an event. So in the light of this, we define an event as follows. So now we will learn definition of event. So what is the definition of event? So we already discussed an event is basically subset of sample space. Okay, so any subset E of a sample space S is called an event. So what is the definition of event? Any subset E of a sample space S is called an event. So this is the definition of event. Okay, so note this definition of event. So now we will discuss occurrence of an event. So for clearing this, we consider here the experiment of throwing a die. Okay, so throwing a die is an random experiment. Okay, so we are considering here experiment of throwing a die. So first of all, we let E denotes the event. A number less than 4 appears. So what is the event E? The event E is nothing but a number less than 4 appears in a die. And if actually one had appeared on the die, then we say that event E has occurred. Okay, so 1 is less than 4. Okay, this number is less than 4. So if 1 had appeared on the die, then we say that event E has occurred. So as a matter of fact, if outcomes are 2 or 3, okay, so 2 and 3 are also less than 4. Okay, so 2, if we get outcomes 2 or 3, then we say that E has occurred. Okay, so thus the event E of a sample space S is said to have occurred if the outcome omega of the experiment is such that omega belongs in event E. Okay, so if the outcome omega is such that omega does not belongs in E, then we say that event E has not occurred. So when the event when a event occurred, so if the outcome omega of the experiment is belongs in that event, then we say the event has occurred. If the outcome omega is not is such that omega does not belongs in E, then we say that the event E has not occurred. Okay, so now we will discuss types of events. Okay, So types of events can be classified into various types on the basis of elements they have. So on the basis of elements, we will classified we will be classified events into various types. So type 1, impossible or sure event. So what does mean impossible? So impossible mean not able to happen. Okay. So an event is called impossible event if the event is not able to happen. Okay. So that case the event is called impossible event. Okay. And what is the definition of sure event? So if an event is guaranteed to happen, then that event is called sure event. Okay. So the empty set, so we know about empty set. So what is the definition of empty set? So we have studied one set chapter about empty set. So empty set is that set where is no element. So if a set has no element, then that set is called empty set. An empty set is denoted by phi. Okay. So empty set is denoted by phi, and the sample space is describe event. So phi and sample space is basically both are subset of sample space. Okay, so phi is subset of sample space, and sample space is itself subset of is s. Okay, so phi and sample space is describe events. So in fact, phi is called an impossible event. So if an event is not able to happen, then that event is called impossible event, and it is denoted by phi. Okay, and if an event is guaranteed to happen, then that event is called sure event. Okay, and sure event is denoted by s. So s, that is the whole sample space, is called the sure event. So to understand this, let us consider the experiment of rolling a die. So we are considering here the experiment rolling of a die. Okay. So what is the associated sample space of rolling a die? So the associated sample space is basically is equal to 1, 2, 3, 4, 5, 6. Okay. So set 1, 2, 3, 4, 5, 6 is basically the associated sample space of rolling a die. Okay. So let E be the event. So we are letting here E be the event. So which type of event E is here? So the event E is basically the number appears on the die is a multiple of 7. So E be the event, and E describes here the number appears on the die is a multiple of 7. So can you write the subset associated with the event E? So write the subset associated with the event E. Okay, event E here describing the number appears on the die is a multiple of 7. Okay. So clearly no outcome satisfy the condition given in the event. Okay. So in this event we are taking that number which appears on the die is a multiple of 7. So no element of the sample space ensure the occurrence of the event E. Okay. So there is no element there is no element on the die which is a multiple of 7. Okay. So here the event has no occur. So thus we say that empty set only correspond to the event E. Okay. So we the event E is equal to basically phi. Okay. So because there is no element of sample space ensures the occurrence of the event E. Okay. So in other words, we can say that it is impossible to have a multiple of 7 on the upper face of the die. Okay. So if we uh, tossing a die, okay, if we uh, if we if we take a die, okay, and there we get rolling a die, okay, if we rolling a die, then we get in random sample space 1 2 3 4 5 6, okay. And you can easily see here there is no element which is multiple of 7, okay. So this is not possible to happen, okay. So that's the even E is basically phi, and E equal to phi is an impossible event. That means the event E is not able to happen, okay. So that is why we take here E is equal to phi. Now let's take up another event F. So we are taking another event F, that is basically the number turns up is odd or even, okay, odd or even. So we know about what numbers. So 1 3 5 7 etc are basically are called odd number, and 2 4 6 8, these numbers are called even numbers, okay. So we are taking event if as the number turns of is odd or even, okay. So clearly if is equal to 1 2 3 4 5 6, okay. That is basically equal to sample space, okay. So if event is equal to sample space, that is all outcomes of the experiment ensures the occurrence of the event if, okay. So if we rolling a die, okay, then either we can get an odd number or an even number, okay. So it is always possible to happen, so it is guaranteed to happen always, okay. So that's the event if is equal to s is a pure event. So if equal to s is a pure event, and the event E is an impossible event, okay. So impossible event means is not able to happen. Pure event means is able to happen, is guaranteed to happen, okay. So second type, simple event. So what is the definition of simple event? So what does mean simple? So if an event E has only one sample point, okay. So the element of sample space is basically called sample point, okay. So if an event E has only one sample point of a sample space, then it is called a simple or elementary event, okay. So what is simple or elementary event? So for remembering, you should remember simple mean one sample point, okay. Simple means one sample point. So if an event E has only one sample point of a sample space, then it is called a simple or elementary event, okay. So in a sample space containing n distinct elements, okay. Suppose we are taking a sample space which consists in distinct elements, okay. So there are exactly n simple events, okay. So we can make event taking one element at a time, okay. So then we will get n simple events. So for example, in the experiment of tossing two coins, okay. So a sample space is basically S equal to HH, comma HT, comma TH, comma HT. Okay, TT. Okay. So if we take a random experiment tossing two coins, okay. So we are tossing two coins, and that case sample space S is basically HH, comma HT, comma TH, comma TT. Okay. So there are four simple events corresponding to this sample space. Okay, they are basically HH, one simple event, HT. Okay, set HT is one another simple event, and set TH is also a simple event. Okay, and set TT is also a simple event. So there are four simple events corresponding to the sample space is. Okay. So these are E1 equal to set HH, E2 is equal to set HT, E3 is equal to set TH, and E4 equal to set TT. Okay. So E1, E2, E3, and E4 are simple events. Okay. Clear? So if an event E has only one sample point of a sample space, then that event is called simple event. Clear? So now we will discuss compound event. So what does mean compound event? Okay. So compound. So if an event has more than one sample point. Okay. So compound event is nothing but opposite of simple event. Okay. So in simple event, there there is only one sample point. But if an event has more than one sample point, then it is called a compound event. Okay. So in compound event, there is more than one sample point. So for example, in the experiment of tossing a coin thrice. Okay. So we are tossing a coin three times. Okay. So then what is the sample space of tossing a coin thrice? So here the events E exactly one head appeared. Okay. So event E exactly one head appeared, and event if at least one head appeared. Okay. And event G at most one head appeared. Okay. So note these events, and E, F, G. Okay, these three events are all compound events. Okay, so the subsets of A's associated with these events are, so E event you can find easily E event exactly one head appeared. Okay, so E event is basically set HTT comma THT comma TTH. Okay, so HTT, THT, and TTH are the only sample point of a sample space. Okay, which is occurred. Okay, towards the event E. Okay, so event E is nothing but HTT comma THT and comma TTH. And the what is the event if? So even if describes at least one head appeared. Okay, so HTT, THT, TTH, HHT, HTH, T double H, and HHH. Okay, these these sample point are in F event F. Okay, and the event G equal to TTT, THT, HTT, and comma TTH. Okay, so at most one head appeared. So here you will get sample point TTT, THT, HTT, and TTH. So here we can see each of the events have more than one sample point. Okay, so E has three sample point. Okay, F has how many sample point F has? So here you can count easily. So F has seven sample point. Okay, and how many sample point in event G? So G has four sample point. Okay, so EFG, each event has more than one sample point. Okay, so each of the above subsets contain more than one sample point. Hence, they are all compound events. Okay, so E, F, and G are all compound events. Clear, students? Now we will discuss algebra of events. Okay, so in the chapter one sets, okay, we have we have studied about different ways of combining two or more sets, visual union, intersection, difference, complement of a sets, etc. Okay, so there we have studied about union of two sets, intersection of two sets, difference of two sets, and complement of a set. Okay. So similar manner, we will see, we will learn algebra of events. Okay, that means we will learn union of two events, intersection of two events, difference of two events, and complementary event. Okay, so likewise, we can combine two or more events by using the analogous set notation. So let ABC be events associated with an experiment whose sample space is S. Okay, ABC are basically events associated with this experiment whose sample space is S. Okay, so complementary event. So for every event A, there corresponded another event A called the complementary event A. Okay, so complementary event means uh, if A is event, okay, so if A is not, okay, so not A event is called basically complementary event. Okay, so for example, take the experiment of tossing three coins. Okay, so take this experiment tossing three coins. So what is the associated sample space of tossing three coins? So the associated sample space of tossing three coins is S equal to set HHH, comma HHT, comma HTH, comma THH, comma HTT, comma THT, comma TTH, comma TTT. Okay. So this is the associated sample space of tossing three coins. So now let A equal to set HTH, comma HHT, comma THH. Okay. So A be the event only one tail appears. Okay. And clearly for the outcome HTT, the event A has not occurred. Okay. So the outcome HTT, the event has not occurred, but we may say that the event not A has occurred. Okay. So thus with every outcome which is not in A, so we say that not A occurs. Okay. So if an outcome which is not in A, then we can say that outcome is in not A. Okay. So that's the complementary event basically called not A to the event A is basically A complement. It is denoted by A complement or A prime. Okay. So here you can see HHH, HTT, THT, TTH, and TTT. Okay. This sample point is not in A. Okay. So if we take collection of these sample point, then we will get not. Okay. So not A is this, or we can define A complement as omega such that omega belongs in sample space, but omega does not belongs in event A. Okay. So we take that sample point which is in sample space but is not in set A. Okay. So if we take that event, then that event is called complementary event. Okay. And it is denoted by S minus S difference A. Okay. S difference A. So A complement is nothing but S difference A. Means um, the sample point belongs in S but not belongs in set event A. Okay. Now the event A or B. Okay. So recall the union of two sets A and B. So union of two sets A and B is denoted by A union B. So what is that? What does mean A union B? So A union B contains all those elements which are either in A or in B or in both. Okay. So this is how we define union of two sets. So when the sets A and B are two events associated with a sample space, okay, then A union B is the event either A or B or both. Okay. So this event A union B is called A or B event. Okay. So therefore, event A or B is denoted by A union B, and it is defined as set omega such that omega belongs in A or omega belongs in B. Okay, this is how we define A or B event. Clear? So now the event A and B. Okay, so we know that intersection of two sets. So the intersection of two sets is denoted by A intersection B. Okay, so the intersection of two sets A intersection B is the set of those elements which are common in both A and B. That is, which belong to both A and B. If A and B are two events, then the set A intersection B denotes the event A and B. Clear? And thus, A intersection B, okay, the event A and B is defined as A intersection B equal to set omega such that omega belongs in A and omega belongs in B. So, for example, in the experiment of throwing a tie twice, okay, so we let here A be the event, score on the first throw is 6 and B is the event, sum of two scores is at least 11. Okay, so then event A is equal to basically 6 comma 1, 6 comma 2, 6 comma 3, 6 comma 4, 6 comma 5, 6 comma 6. Okay, so A is basically event, score on the first throw is 6. Okay, and B is the event, sum of two scores is at least 11. So B event is basically 5 comma 6 comma 6 comma 5 comma 6 comma 6. Okay, so A intersection B equal to basically uh, you have to find here common sample common element in A and B. Okay, so you can observe here 6 comma 5 and 6 comma 6. These two elements are in A and also in B. Okay, so A intersection B equal to set 6 comma 5 comma 6 comma 6. So note here that the set A intersection B, okay, that 6 comma 5 comma 6 comma 6 may represent the event. The score on the first throw is 6 and the sum of the scores is at least 11. Okay, so this event represent the event. The score on the first throw is 6 and the sum of the scores is at least 11. Clear, students? So the event A but not B. So we know that A difference B is the set of all those elements which are in A but not in B. Okay. So therefore, the set A difference B may denote the event A but not B. Okay. And we know that A minus B, A difference B. Okay. This is basically equal to A intersection B complement. Okay. So A difference B can also be written as A intersection B complement. Okay. So this is called A but not B event. Clear? So now we will discuss example number 1. So here we consider the experiment of rolling a die. So let A be the event getting a prime number and B be the event getting an odd number. So write the sets representing the events A or B, then A and B, and then A but not B and not A. Okay. So students, uh, try to write the states according to the given information in this example. Okay. So first of all, think about this. How would you approach this example? So let us see solution. Here the sample space is S is basically equal to 1, comma 2, comma 3, comma 4, comma 5, comma 6. Okay. And event A. Event A is nothing but that event we're getting a prime number. Okay. So event A is nothing but 2, comma 3, comma 5, and B event is the event getting an odd number So event B is basically equal to set 1, 3, 5. Okay, clear? And obviously, A or B. Okay, A or B means A union B. So take that element which is in either A or B or in both. Okay, so A or B event is nothing but A union B, and this is equal to set 1, 2, 3, 5. Okay, so A or B event is basically 1, 2, 3, 5. And A and B. A and B means A intersection B. So now we take common element in A and B. Okay. So here you can see 3 and 5. These two elements are in A and also in B. Okay. So A and B event, that is A intersection B, equal to set 3, 5. And then A but not B. So we have to take here those elements which can in A but not in B. Okay. So A difference B is, you will get singleton set 2. And then not A. Okay. Not A means A complement. Okay. So A complement means we will take those elements which is not in A but in sample space S. Okay. So here you can see 1, 4, 6 are not in set A but in A in sample space S. So A complement is equal to set 1, 4, 6. So I hope this example is clear to all of you. Okay. So now we will discuss mutually exclusive events. So what is the definition of mutually exclusive events? Okay. So in the experiment of rolling a die, okay, we are rolling a die and a sample space is basically S equal to set 1, 2, 3, 4, 5, 6. Okay, and consider events here. A an odd number appears and B an even number appears. Okay, and clearly the even A excludes the even B and vice versa. Okay, even B excludes the even A. So in other words, there is no outcome which ensures the occurrence of events A and B simultaneously. Okay, so A and B event cannot occur simultaneously. So here, A is basically 1, 3, 5 and B is 2, 4, 6. Okay, so clearly here, intersection of A and B is basically P. Okay, that is A and B are disjoint sets. So in general, two events A and B are called mutually exclusive events if the occurrence of any one of them excludes the occurrence of the other event. Okay, that is that they cannot occur simultaneously. So in this case, the sets A and B are disjoint, means intersection of A and B is empty. So again, in the experiment of rolling a die, consider the event A an odd number appears and event B a number less than 4 appears. Okay. So in this case, the event A is 1, 3, 1, 3, 5 and the event B is 1, 2, 3. Okay. So now here you can say 3 is in A as well as 3 in B. Okay. So therefore A and B are not mutually exclusive events. So here, remember, simple events of a sample space are always mutually exclusive. Okay. So if we take intersection of two simple event, then you always get empty. Okay, set. Okay, of a sample. So simple events of a sample space are always mutually exclusive events. Clear? So now we will discuss exhaustive events. So for understanding exhaustive events, first we consider the experiment of throwing a die. Okay, so we have here sample space A is equal to set 1, 2, 3, 4, 5, 6. Okay, and let us define the following events. A is in a number less than 4 appears. B event a number greater than 2 but less than 5 appears. And the event C a number greater than 4 appears. Okay. So then here event A is 1, 2, 3 and event B is 3, 4 and event C is 5, 6. Okay. So we observe that Here, A union B union C is nothing but basically is equal to sample spaces. Okay. So if we take union of three sets A, B, and C, then we take here, we get here sample space S. Okay. So such events A, B, C are called exhaustive events. Okay. So A, B, C, these three events are called exhaustive events. So taking by taking union of A, B, C, we get sample spaces, and this type of events are called exhaustive events. Okay, so in general, if we have n events E1, E2 up to En, okay, of a sample space S, and if union of E1, E2, E3 up to En, okay, that is union I equal to 1 to n, Ei equal to S, then these events are called exhaustive events. Okay, then E1, E2 up to En are called exhaustive events. In other words, we can say E1, E2, E3 up to En are said to be exhaustive if at least one of them necessarily occurs whenever the experiment is performed. Okay, and further, if Ei intersection Ej is empty, okay, for I not equal to j, then events Ei and Ej are called pairwise disjoint. Okay, and if we take union of ei, then I equal to 1 to n, then this is equal to s sample space s, then events e1, e2, en are called mutually exclusive and exhaustive events. Okay, so what is the condition for being mutually exclusive and exhaustive events? So the condition for that is basically ei intersection ej is phi, where I not equal to j, and union of ei I equal to 1 to n is S. Okay, then E1, E2 up to En are called mutually exclusive and exhaustive events. Clear, students? Now we will discuss NCERT example number 2. So first of all, read the example very carefully. So two dice are thrown and the sum of numbers which come up on the dice is noted. Okay. So let us consider the following events associated with this experiment. So A is even, the sum is even. Okay. And B is the event, the sum is multiple of 3. And the event C is the sum where the sum is less than 4. And even D, the sum is greater than 11. Okay. So which pairs of these events are mutually exclusive? Okay. So you have to find pairs of these events which are mutually exclusive. So students, first of all, think about this. How would you approach this example? Okay. So then we will see solution here. So there are 36 elements in the sample space S. Okay. And sample space S is defined as set of pair, order pair x comma y, so that x comma y belongs in 1, 2, 3, 4, 5, 6. Clear? And then even a. Even a is basically sum is even. Okay. So we can take this type of whatever 1 comma 1, 1 comma 3, 1 comma 5, 2 comma 2, and so on. Okay. So this type of whatever you can take in even a. And the even b is basically the sum is multiple of 3. Okay. So sum is multiple of 3 means it might be 3, 6, 9. Okay. And 12, etc. So B event is basically order set of order pair 1 comma 2 comma 2 comma 1 comma 1 comma 5 comma 5 comma 1 and so on. Okay. And the event C, the sum is less than 4. Okay. So you can take here 1 comma 1, 2 comma 1, 1 comma 2. Okay. So if you take sum of sum, then you will get for first one 1 comma 1, you will get 2, 2 comma 1, you will get 3, 1 comma 2, you will get 3. Okay. So all are less than 4. And D, the sum is greater than 11. So you will get only 1.6 comma 6. For that, the sum is greater than 11. So the D set, D event is basically equal to singleton set 6 comma 6. So we find that A intersection B. Okay. So A intersection B, you will get 1 comma 5, 2 comma 4, 3 comma 3, 4 comma 2, 5 comma 1, 6 comma 6. Okay. So A intersection B does not 5. Okay. Doesn't it equal to 5. So the A and B is not disjoint, are not disjoint. Okay. So therefore, A and B are not mutually exclusive events. And similarly, you can find A intersection C, that is not also empty set. Okay, and you can find A intersection D, that is not also empty set. B intersection C, that is not equal to empty set, and B intersection D is also not equal to empty set. Okay, thus the pairs of events A comma C, A comma D, B comma C, B comma D are not mutually exclusive events. Okay, so students, try to find A intersection C, A intersection D, B intersection C, and B intersection D. Okay, and now you can easily find C intersection D. So in C intersection D, there is no common element. Okay, so C intersection D is empty set. So C and D are mutually exclusive events. Okay, so C and D, these two events, these pairs are mutually exclusive events. Clear? So now let us move on to the next example. So in this example, see, a coin is tossed 3 times. Okay, and then consider the following events. A is no head appears, B is exactly 1 head appears, C at least 2 heads appears. Okay, so do they form a set of mutually exclusive and exhaustive events? Okay, so students, first of all, try it yourself and then see solution. So the sample space of the experiment is S equal to HHH, HHT, HTH, THH, HTT, THT, TTH, TTT. Okay, this is the sample space of the experiment. Okay, and event A is basically no head appears. Okay, so event A is nothing but singleton set TTT, and event B exactly 1 head appears. So event B is equal to set HTT, THT, TTH. Okay, and the event C is basically at least 2 heads appears. So event C is basically set HHT, HTH, THH, HHH. Okay, now A union B union C is nothing but sample space S. Okay, so A union B union C is equal to sample space S. And therefore here A and B and C are exhaustive events. Okay, and you can find easily A intersection B is phi. Okay, A intersection C is phi, and B intersection C is also phi. Okay, so you can easily calculate A intersection B, A intersection C, and B intersection C. Okay, so students, find A intersection B, A intersection C, and B intersection C. Okay, so therefore the events are pairwise disjoint. Okay, so since A intersection B is phi, A intersection C is phi, and B intersection C is phi, so the events are basically pairwise disjoint, and that is they are mutually exclusive. Okay, so hence A, B, C form a set of mutually exclusive and exhaustive events. Okay, so A, B, C, these 3 events are a set of mutually exclusive and exhaustive events. Clear, students?